So let's continue with this very sketch group theory review, the second lecture. And in the first lecture, we discussed a lot about group presentations. And specifically, we looked at two equivalent group presentations for D4. So these two equivalent presentations, this is the one that we found in the Group Explorer, which we'll talk about some more. And with the little caveat that the Group Explorer uses this RFR equals F inverse, but with the involution on F, we can just write that as FRFR equals I. And frequently this would be FR squared equals I. Oops, that's not FR squared, sorry. Just FR squared equals I, right? So that's one group presentation, but we showed that there's this equivalent presentation, which I'm just going to call the coexter presentation, because eventually we're going to really lean into this idea of the coexter group. So we decided that this is the most abstract way. This, for us, is going to be the most abstract way to define a group, because, you know, just looking at this, it's pretty abstract. I mean, if somebody just gave this to you and you had to think about it without writing anything down, I'm not sure that a lot would come of your analysis of just this sort of string of letters and symbols. But the idea being that between these different words, and they're called words, that's the literal correct use, when you construct words from R and F, and if you create arbitrary words, such as, say, this word, where here's a little piece of it, and it's a finite word, though, it's not an infinite word. By using these relations in here, this is the generators and these are the relations. By using these relations, you can start cutting this word up, you know, cutting things out, cutting out the 4 R's to be an I, the 2 F's to be a flip, and then you can take the RFR and turn that to an F inverse. And by the time you do that, you end up with just a tight little set of groups elements, 8 total, right? And the multiplication table for D4 is given here, and this is taken directly from the Group Explorer, and we kind of look through this. And this is clearly done using the generators R and F, but we could have turned it into F and D, where D is a diagonal flip. And if I recall correctly, F and D, where we leave F alone, of course, and then I think D becomes one of these guys is D, and then you can change everything into F and D. But the group structure is the same regardless of the presentation, but the multiplication table does look a lot different. The point being that we now have settled on our abstract notion, and everything other than this is going to be some form of realization, the group, right? And if that realization means each element is going to be completely, I guess what we could say is, for the purposes of our stuff, is this is the abstract form, and anything where we actually enumerate all the group elements is going to be a realization, right? So even this would be some form of realization, because every group element has been enumerated, right? You know, this is just the way I want to use the word realization. The point is that a representation will be a realization that uses matrices, right? Matrices. So that's where we're headed. We're ultimately heading to a representation theory, but we're going to go through group theory right now. And we're really going to be studying different ways of looking at the groups, realizing the groups. But we're going to keep everything in this very abstract form here. And then when we pop out of this little subsection, we can go into our representation theory. Okay, so let's go on. So when I was studying group theory, I certainly didn't have a Group Explorer. I had a textbook with a lot of abstract markings in it that I fought my way through. And I actually think I would have learned group theory very differently had I had the Group Explorer when I started this. And in some sense, what would I have done differently in my mind? How would my mind have connected this stuff? Well, the first thing about the Group Explorer that really jumps out at you is that it enumerates every group. And it does so in sequence by their order, meaning how many elements the group has. So the first thing you kind of if you really if you do a group explorer-centric education on group theory, what you tend to do is you tend to think of all the groups at once. But when I learned group theory, it was like, here's a group theory principle, here's an example of a group. Here's a group theory principle, here's an example of a group. Here's a problem involving some of the groups you've already seen. And you kind of start hovering around some critical groups like D4, the dihedral group, which ironically we're going to hover around today. You might hover around V4, the symmetries of a rectangle, right? This would be the symmetries of a square. This is the symmetries of a rectangle. So, when you study group theory the classic way, you kind of pick out groups. Oh, there's the symmetric group on order 3. This is a cyclic group because it's got prime order. And you kind of like get real spotty, and you kind of lose this picture that all the groups have been enumerated, and you can kind of think of the groups as numbers, right? Just like you would think of 1, 2, 3, 4. You think of a whole integer number line, 0, -1. Think of all the numbers at once. In some sense, thinking of groups, you should think of all the groups at once as one big body of groups that have all been classified. Of course, it's harder because the classification of the groups is much more abstract, and these group presentations have to be hunted down. You can't go from a group of order 7 to a group of order 8 by adding 1. It's not that easy at all. It's not even fair to say it's not that easy. It's literally not a thing, right? You have to find all the groups of order 8. The word is you have to classify all the groups of order 8. And the fact that there are 1, 2, 3, 4, 5 groups of order 8 and one group of order 7, that's a deep fact, actually, in mathematics. So this approach, this rough, quick approach to group theory, I kind of want to use that angle, that all the groups are enumerated, and think of all the groups at once. And today, we're going to focus a little bit on some of the classics. We're going to focus on D4. Ultimately, we're going to focus on V4. By the way, these have different names. V4 is also Z2, direct product, Z2. And sometimes people literally use this as the name of the group instead of naming the group and showing that it has this decomposition into a direct product of two other groups. We'll talk about that in a future video. But eventually, although D4 is important because we're talking ultimately about Lie groups in this course, and D4 is an example of a coextra group, which I feel like is an important subject, I really do want to dig into this cool group here, right? That's a really, wait a minute, not that one, which is the really cool one. I want to do, I think it's this one here, right? It's sometimes it's called T, right? T. And just do some examples of some groups that are of higher order than you normally see and just sort of unpeel those groups a little bit. But we're going to start today with just D4, and we're going to review some of the ideas of different types of subgroups of D4. Okay, so let's begin. So now let's look at some of the data that just flows right out of the Group Explorer. What you can see is we automatically get the multiplication table, and the multiplication table is written in the language of the presentation. So the generators were R and F. So everything in here is going to be a word in terms of R and F, right? So that's easy to see, and so it's very presentation dependent in that sense. But the multiplication table for D4 is the first thing jumps out at us. Then you can have the multiplication table written in this broken up form in terms of cosets and subsets. So we'll talk about subsets first, and then we'll come back to this multiplication table. What I want to spend some time on today is this list of subgroups. So that's really important and convenient, is to know all the subgroups of a group. It talks about the object of symmetry for the group, which, very important point to understand, is not every group has an object of symmetry that you can just draw down. So it's not a good idea to think of groups in terms of their objects of symmetry. It's really, D4 is really a bad example to lead with, if that's my point, because it's so, this is obviously rotations and flips in D4, but not all groups have an object of symmetry you can draw, although they all presumably have an object of symmetry, even if that object of symmetry is higher dimensional and hard to describe and maybe not even known. The presumption is that there's some symmetry object out there that remains invariant in shape, at least, even if
we can't visualize it. Now notice they color the indices here. They color the corners on this object of symmetry, which seems like, oh, well, that breaks the symmetry, right? Because if I rotate the square, then this becomes green, this becomes red, and that's not the same. But so there is a temptation for a tendency for students early in the subject to realize, well, wait a minute, to confuse the object of symmetry with permutations of these vertices on the object of symmetry. And we want to think of groups in terms of permutations sometimes. And to do that, we have to label all of the points. So we really want to work out the difference between the object of symmetry and the nature of a group as a set of permutations. And that's what this coloring causes some confusion. So that's something we need to focus on. The cycle graph is really an important way of interpreting how the group, how group operations act and the different possible subgroups. This helps us look for subgroups, which is an important thing. We won't talk about that one today. And then, of course, the Cayley diagram is probably the most useful way of studying the structure of a group, because it kind of reveals all the subgroups and it reveals the generators, right? And there's a lot to the Cayley diagram. But for today, we're just going to focus on these subgroups for now. And then we'll kind of hit all these other topics later. So the point is that we are shown all of the subgroups of the group, and they're listed out here with their own presentations. The generators are all that you need to present the subgroups because the relations are still the same. It's always true that that R4 equals F squared equals RFR, well, I guess FR equals I, right? This is the presentation, and that's true always. So if you're dealing with a subgroup, you can kind of leave that out because the presumption is that you know the relations for the group. But this is always going to be true. So now all you need to do is talk about what are the generators of the subgroups. And then once you know that, this list is saying, well, there's 5 subgroups of order 2, right? And there's 3 subgroups of order 4. This is a good point to remind you of Lagrange's theorem, right? Very famous point, but the order is something you should remember. The order of a subgroup always divides the order of a group. So if we're dealing with a group with 8 elements, we know the subgroups can only be of order 1, 2, 4, or 8, right? And sure enough, we have 5 groups of order 2, and we have 3 groups of order 4. Now, it doesn't mean there has to be. So the requirements on how many groups of what different orders, that's a deeper part of group theory, usually involving things called the Silo theorems and maybe a few other ideas. But for now, just remember Lagrange's theorem is part of our review of group theory. Obviously, the group itself has order 8, and the trivial subgroup has order 1. So in this case, all 4 of these factors are accounted for, but that's not a requirement. So why don't we list them all out? Let's just list them all out for this group. So here are the 5 subgroups of order 2. That's these guys right here, right? They're very easy. They're all involutions. Remember that word? The reason involution is a word I like to harp on is because it represents reflections, and reflections are an important part of the idea of a coextra group, which is something we have to talk about down the road. But all these involutions are pretty straightforward. Notice that they all, of course, since they're subsets, they all share the identity element as one element, but otherwise these are different subsets, so they're of order 2, so they can't share any other element and still be unique. So now let's look at the ones of order 4. And let's see if I got this right. The group of order 4 is all these rotations, r squared, r to the 4th. Whoops, I got that wrong. It's not r to the 4th, it's r to the 3rd. Because remember, r to the 4th equals the identity from the properties of the dihedral group. Maybe I should write those down just to remind us. So here I'll box these. These are the relations. So this is just, I'm looking for groups of order 4. Those are the only, if there's any, these are all the subgroups of order 2. These are supposedly groups of order 4. They can only be order 4. There's no other allowed order by Lagrange's theorem. So we have this obvious subgroup of the 4 rotations, and then we have these 180-degree rotations and the flips, and these are all in the group. This one here, r squared FR, and then I wrote r squared FR, which is obviously the product of the two generators, right? R squared FR, this is the two elements given that generate the group. So obviously the product is in the group, but that's not part of the word list that we use on the multiplication table. You don't see r squared FR in here anywhere. And that just shows you that we need to do a word reduction, right? So we would write r squared FR equals RRFR, but RFR, right, through this part of the presentation, right, r squared FR equals RF, right? So I can take this and I get, I erase that and I get RF, which is different from FR, okay? So now we have found the proper subgroups, right? We found all the proper ones because they're strictly contained within and not equal to the group itself. And I guess the trivial group counts as a proper subgroup, but I found all the proper non-trivial subgroups, right? And believe me, I didn't find them. The Group Explorer did, and they gave me all the information I needed to enumerate them. So now, armed with this, I can find a very important diagram that's actually and oddly not given in the Group Explorer. I actually had to go to Mathematica to develop it, or to find an example of it, but it's called the subgroup lattice. The subgroup lattice. So I'll just say subgroup lattice. And the subgroup lattice is actually a really very important way of visualizing subgroups. And I want to have a look at it for D4. So here in this little Mathematica program, which I was able to get right off the web. I mean, I didn't write this. Somebody else did. It was really nice. It doesn't show every group out there. It's not as comprehensive, this little program, but it's got the ones that we care about right now, and it certainly has D4. So this is the subgroup lattice of D4, and if you had the program and if you put your mouse over any of these things, it would tell you exactly what the subgroups are. But the point is the way you construct a subgroup lattice is just by inclusion, because all of these subgroups are subsets of our group. So our group is D4, and certainly Hn, whatever n is, through 0 through 9, is a subgroup of D4, right? It's a subgroup of D4, which is sort of written this way. If it's possible that Hn equals D4, you throw in the little equal sign there, and that's certainly true in this case. So D4 is up here. Well, let me do this in black. D4 is up here, and the lines mean subset inclusion. So this is a partially ordered set, or these are posets, right? Or I should say the set of all subgroups is a poset, right? Is a partially ordered set by set inclusion, right? So there is a set out there of all the subgroups of this group. Well, let's think of it this way. The group itself is a set, and because the group is a set, you can think of its power set, right? The power set is the set of all possible subsets of D4. We're not interested in the power set. We're interested in the set of all the subgroups of D4. So that's a set with 9 elements in it, right? So the set of all subgroups is a set of 9 elements, and you can create an ordering by set inclusion, but it's only a partial ordering. So this set of all 9 elements, is a poset, meaning it's a partially ordered set where the ordering is set inclusion. Anyway, so with that in mind, D4 is certainly the one up here that includes everything because it's the full set, so all subsets are included in that. And then these guys here are going to be the 3 subgroups of order 4. So I can write them down like this. Now the subgroups of order 4, if we go back to our list, it's obvious that these various subgroups of order 4 contain these subgroups of order 2 in various combinations, right? This one here certainly contains, I guess I shouldn't say this one, I can actually name it, right? So this guy is H6, right? So this is H6, and H6 certainly contains H1, And this guy here is H7, right? And H7 certainly contains H2, et cetera, et cetera. So there's, these subgroups are subgroups of other subgroups of the set. And that's exactly what the lattice is supposed to tell us. Whoops, I think I made a mistake here. This guy here in the middle is it's a subgroup of order 4s. I've gotten rid of these. I'm getting sick of writing these little brackets, so I'm getting rid of them and just writing the generators down. Man, actually, I really screwed that up. I think I got it straight now. So this is obviously a subgroup of order 4. These two are the subgroups of order 4 based on these generators. And clearly the subgroups of this, you can form R squared F, which is the horizontal flip. This is the regular flip, and this is the 180-degree rotation. The only subgroup of R is going to be the 180-degree rotation, and then this one's going to have the 180-degree rotation and the two diagonal flips. And so these are all the involutions, and this is the whole group. And of course, at the bottom of this whole thing is the identity group. So I find this to be a very valuable way of studying a group and looking at its structure straight through its subgroup diagram. There's so many things about subgroups that are important that this to me is the most important thing. And it's funny because the Group Explorer doesn't just lay it out for you. It lays out a lot of other things, but it leans on the Cayley diagram. Okay, fair enough. I mean, I'm sure there's a good reason. The people who invented the Group Explorer teach this probably every day. They're professionals at it. So their emphasis is the Cayley diagram. And I think that's probably a good idea because the reason that's good for teaching is because the Cayley diagram talks about the group actions. If you start at the identity and you multiply on the right by R, you get to the element R. You multiply again, you get to R squared. This actually sets you up for understanding group actions, which is how these actions can happen on other sets. And that's really important to prove the basic results of group theory, like Lagrange's theorem can be proven using group actions, and the orbit stabilizer theorem only exists in context of group actions. So my subgroup lattice, which I think is a great way of visualizing the structure of a group itself, is not a great launching point for understanding group actions, which is an important part of elementary group theory's proof system. Okay, but that aside, let's finish up about the subgroup lattice. So as part of our review, we've now understand the subgroup lattice, the nature of subgroups, but you see that the Mathematica gives you these buttons. And these buttons are a pretty good hint that this is an important thing to know. What are cyclic subgroups, what are normal subgroups, and what is the center? So let's make sure we get through that in this lecture. So we're going to show why H7 is a normal subgroup. I've listed the normal subgroups here in green. Notice all of the guys of order 4 are normal, and this one particular subgroup of order 2 is normal. There's a reason why all of these subgroups of order 4 are normal, and we'll get to that in a moment. But let's just look at H7. That's this one right here, right? And there it is listed out. Those are all the elements of H7. Now, to show that this subgroup is normal, there's two ways of doing it. There's actually more than two ways of doing it, but these are the two that we'll talk about right now. One is that they're self-conjugate. This subgroup is self-conjugate, and the left cosets of this subgroup equal the right cosets. And this is a little absurd because these are both the same idea, right? If I write self-conjugate, what I mean is I'm taking the entire set H, and I'm going to take every element of the set H and multiply it by some other element of the group, G, on the left, and then on the right, I'm going to multiply it by some element of the same element's inverse. And if that set equals H for all G, right, for every G in the set, the larger group, which in this case, we're talking about D4, right? So I guess in our case, we're talking about H7, H7, and D4. Then we are dealing with a normal subgroup. But obviously, if I multiply this expression on the right by G, I just get GH equals, GH7 equals H7G, which is the left coset equals right coset definition. So this is called conjugating H7 by G, and conjugation obviously implies that all of the left cosets of G equals the right cosets of G. So in case it isn't clear, the coset idea is I'm going to take the set H7 and I'm going to multiply every element on the left by G in this case here, using this example. And that will tell me the a left coset of H7, or the left coset of H7 by G, right? So if I were to do that, that's right. Let's just calculate, say, first of all, if G is an element that's already inside of H7, then clearly this is satisfied, right? Because it's a subgroup. So if I multiply every element in here by R squared, I'm just going to permute them, right? This is a way of saying I'm acting on the subgroup H7 by one of its own elements. All you do is permute it, so it's very clear that I could do that on the left or the right. So this is satisfied for every element of G that is inside of H. It's satisfied, or H7. So I'm only interested in the ones that are not inside there. So for example, R, right? R is not an element of H7. So I can now find the left and right cosets of H7 relative to R. And here they are. And the only question that comes up is about these last two elements, right? They're not part of our normal words, so I have to I have to go in and break them down. So I break down the word R cubed F, right? I'm breaking down this guy. And R cubed F is R squared F, but R squared commutes with everything, right? So I get R F R squared, which is R F R R, but R F R equals F based on the presentation of the group. So this guy is FR. So I can just erase this and write FR. And it doesn't take much to see that by the similar analysis, this becomes RF here, right? The point being, though, that this set and this set are the same. So R does, in fact, have the property that RH7 equals H7. Why do my 7s all screwed up? RH7 equals H7R, right? So it does have that property. Now, we're not quite out of the woods because we have to, this has to be true for all G, right? Well, not for all G in H7. This has to be true for all little g in D4, right? So we've definitely shown that it's true for the elements of H7 itself, right? So we've shown that it's true for E, R squared, what are the rest of the elements? F, R squared, F, F, R squared, F. And we've also shown that it's now true for R. So in order to be normal, it has to also be true for RF, for FR, and for R cubed, right? So I have to go through this exercise for all of those sets. So I can try this the other way with, I can check the conjugation instead of checking both sets. Why don't I just check the conjugation and see if the conjugation is such that this equals H7. I'm using sort of the other rule. And so by checking RF, which I need to check, right? By checking RF, RF is its own inverse. So RF inverse is going to be E. And then I have to look at, so that's E. Then I have to look at RF, R squared, RF inverse. Oops, I wrote FR there. That should be RF, because RF is its own inverse. And, well, what does that end up being? Well, let's see. RF, R squared, RF, right? This is RF, RF. That is just F, R, R, F, but this is R squared, which commutes with everything. So this is R squared, F squared, which equals R squared. So that is R squared. And the next one is RFFRF, which is R squared F. That's R squared F, which is one of our final words. And then the last one is RF, R squared F, RF. And that's RFRRFRF, which is FFF, which is F, because F squared is just 1. So that becomes F. And sure enough, that equals H7 again. So conjugating H7 through this element RF, still H7. So now I say that RF normalizes H7. Actually, what I say is I say RF and R normalize H7 because I checked R, and R satisfied the normalization rules, and RF satisfied the normalization rules. I'll let you do the others yourself, but sure enough, H7 is normal. We know this not only because we were told, but we just checked. I just checked 2 of them. You can check the 2 others, and you'll see that these rules, either creating the cosets and checking that the left and right coset are equal, or conjugating by the element and seeing that you get your subset back, we can say that RF and R normalize H7, but we can also say that the other missing elements normalize H7. So RF, FR, and R cubed normalize H7. So H7 is in fact a normal subgroup. So now we've gone through the exercise of showing that H7 is a normal subgroup, and you can do it likewise for all of the other supposedly normal subgroups. Now, the part that we are learning, though, is that some subgroups are not normal, right? Let's focus for one quick second on these 4 normal subgroups, those subgroups of order 4, right? Using Lagrange's theorem, we know that if H7, if the order of H7 equals 4, we know that the coset of H7, all the cosets of H7, they have to have size 4 as well, right? So the order of any coset of H7 is also going to equal 4. So what you discover here is that H7 is a subgroup of order 4. So every coset, right, must be also of order 4. So for example, if I write the coset of H7 as GH7, I know that that's order 4. And if I write it as H7G, that's order 4. So the left and right cosets have the exact same order, obviously. That's kind of obvious. But what's interesting is if the group has order 8, and H7 itself has taken up 4 of those elements, there's only 4 elements left. So that means the left coset and the right coset, they both are dealing with the same 4 remaining elements, so they always have to be the same. And that's an important fact on observation, that any subgroup whose order is half the size of the order of the group is going to be normal, right? So you could have seen that these 3 subgroups were normal just by knowing their order, right? So if the order of the underlying group divided by the order of the subgroup in question, if that equals 2, then H is normal in G. And the normal subgroups are given by this little triangle, right? A little triangle facing the direction of the normal subgroup. I guess I could draw that better. I could draw that more like H is a normal subgroup in G, right? So this is an important fact. And the way you say that is you say the index of the subgroup H in the group G is the order of G divided by the order of H. That equals 2, then H is normal in G. And that's because the left and right cosets can only share the same 4 elements, so they have to be the same. Notice that does not apply to H1, right? H1 did not have to be normal, and there are plenty of groups of order 2 that are not, in fact, normal. Okay, so we've reviewed what a normal subgroup is, and going back to this diagram, we see that
in this group, there are 4 normal subgroups. Normal subgroups are really, really important because they describe all of the possible homomorphisms that we can have from this group to other group. It also describes all the possible quotient groups and other really important things. And so the last button you can push here is the easiest one to understand. It's called the center. The center, if we push the center button, we would have gotten, let's see, I think we would have gotten, let me check, we would have just gotten this group here. This is the set of, this is a subgroup, right? All of these are subgroups, cyclic subgroup, normal subgroup. The center is actually a subgroup. So you could call this I guess the central subgroup. I don't know, you call it the center is really what it is. It's always the center, but it's understood to be a subgroup because it is. This is the subgroup of all elements that commute with everything in the group, right? So R squared, this group here is the group generated by R squared. So it is just the set. As a set, it is the group E and R. It is the elements E and R squared. And R squared commutes with everything. So if you have F R squared, that equals R squared F. If you have R squared R, that equals R squared. Well, that's sort of obvious. I guess this is the only one where it really kind of digs in and matters. So that's called the center. And the center is an important group when you start studying the idea of group actions. And lastly, it's something to note while we're on this. Remember, we were talking about treating this group right here and looking at its subgroup lattice, which is now highlighted in red. Now, what's interesting is this is not a normal subgroup of D4, but it is a normal subgroup of the group generated by R squared and F. So if we just broke out this lattice itself and cut away everything else, right? Just chopped away all this stuff. So we were only studying now this group, which is V4. What we discover in that case is that suddenly this is a normal subgroup in V4. So that's an important thing to understand, is that the normality has to do with the group in question, the overall group in question. It is not normal with respect to all the elements of D4, but it is normal with respect to all the elements of V4. And the language for that is that V4, again, is a normalizer, is a normalizer of R squared F. That's the language we use. Now, here we're, instead of an element that normalizes the set, we're looking for the smallest subgroup of D4, that normalizes a given non-normal subgroup. So if all these subgroups down here, I'll just erase, let me erase all the ink, right? So D4 is up here, right? So we have D4, we have R squared F, and we have F. We're looking for the smallest subgroup that contains the subgroup F, and every element of that subgroup normalizes F. And that's called the normalizer of F in G. And it's written as normalizer G of the subgroup H, which in our case, this becomes the normalizer in D4 of the subgroup generated by F, right? And that equals the subgroup generated by R squared F. And we can tell this right away from the subgroup diagram, because the normalizer of a non-normal subgroup, these are all facts that I'm sure you've heard that we've got to just review. The normalizer of any non-normal subgroup is always a subgroup itself of the larger group, right? So the normalizer of F is a subgroup of D4. So there's only 3 subgroups of D4 that could possibly contain F if F itself isn't normal, and only one of them actually does. So this set here must be the normalizer of F in D4. Now, it turns out in this case, this is a normal subgroup of D4, and it is the normalizer of a non-normal subgroup
I guess I was doing normal subgroups in green before, right? But this is a non-normal. F is not normal, but it turns out its normalizer happens to be normal in D4. But that's not a requirement. That's something that's true in this case, but not always. In other words, the normalizer is always a subgroup, so it's always going to appear in the lattice, but it may not actually be normal, right? In other words, we could have had a situation where this it just isn't normal. We'll find a group where that's an example. I'll find a group where that's an example. And in this case, however, what is always true is that if you broke down into this subgroup lattice of just the normalizer subgroup of F, then in fact, F is normal with respect to its normalizer, right? So F will always be a normal subgroup with respect to its normalizer subgroup, but its normalizer subgroup is not necessarily normal in D4. So there's all these little things you got to kind of track when you study this. All right, so what have we done? So today we've gone back and we've really kind of focused on what is my favorite way of looking at a group, which is the subgroup lattice. The group explorer, like I said, leans into the Cayley diagrams a bit. We talked about we talked about cyclic subgroups. We reminded ourselves about normal subgroups, at least their definition, and we reminded ourselves about the center, and we explored D4 as an example of a group that it's got a lot of richness. D4 has a lot of richness, but it's not rich enough to demonstrate the fact I just mentioned, which is that the normalizer of a non-normal subgroup is not necessarily normal in D4. It's not rich enough to show that. So, but it's still pretty rich. It shows a lot of other things. I mean, it certainly shows the idea of forcing normality by having a large enough subgroup, right? If the subgroup is order 4 or half the order of the total group, it demonstrates all of that. Notice, by the way, that, all right, so this guy has order 4, right? And these guys have order 2. So the index of, say, I'll call this set A and that set B, the index of A and B equals 2. So these guys are all normal in their respective supergroups, right? Super subgroups. So that's interesting, but they're not normal with respect to that, right? Okay, hold on. All right, and in the next lesson, we'll just examine another group a little more carefully, review some of these concepts more quickly for a couple different cool groups, and we'll start getting a bit of familiarity with these different groups, the quaternion group, for example, the quaternion group of 8 elements, right? Dihedral group of 8, we're going to kind of see how common these guys are. We're going to kind of look through all of these together and just start sort of working down the group explorer and kind of examining these different groups and spend some time talking about the different things we have to remember for group theory to understand all these different groups.